Okay, class, today we're going to talk about a method called linear approximation. And if you take a look and break that down, we're going to talk about approximating, estimating a value, and doing so using an idea of a line. And we've talked about derivatives of tangent lines during this class. You'll find that our knowledge of derivatives of tangent lines play into how to perform and arrive at a linear approximation for a value. We'll show you a little bit about what this means first of all. What is linear approximation? Well, if you have a function f of x and you have a known value at a certain location, linear approximation is going to assist us in finding a value nearby, in the neighborhood. Because if we can find a tangent line equation at a known value, we're going to find that that tangent line closely resembles the actual curve. Note, the tangent line to f of x at x equals 6 closely resembles the red function of f of x. So if we know the yellow tangent line, we can use that to make an approximation at 6.2. So the little green dot on the tangent line is a pretty good approximation for the blue dot that's actually on the curve. So without any further ado, that might be a little confusing for you. So we're going to take a look first at some examples so we can get a concrete knowledge bank for how to attack a linear approximation problem. Take a look. Number one, we want to use linear approximation to approximate the square root of 37. So the first thing you do is you stop and say, well, I know something nearby. I know the square root of 36. I know the square root of 36 is 6, so the square root of 37 is a little more than 6. I also think rookies that do problems like these, they think, I got an idea. I'm just going to take my calculator and go the square root of 37, shrug my shoulders, put it down to like 3 decimal places, and see if I can, see if the teacher will buy that as an answer. I'm here to tell you that that will not work. This is no calculator, number one. Number two, your final answer will be a fraction, and all correct answers will be identical. So you can't use your calculator and say, wow, that's pretty darn close. I bet the teacher will accept that. A linear approximation is very precise steps that have to take place, and we will all get the exact same answer if done correctly. Here are the steps. You write down that fact that you know, that nearby numeric truth that you do know. I just call this an I know statement. These always start with an I know statement. I know that root 36 is 6. That drives my decision making about the function f of x equals, instead of the square root of 36, we'll make f of x the square root of x. What really this amounts to here is we're going to find a point and a slope so we can find the equation of a line, okay? So I know in order to find the slope, I'm going to have to take the derivative. We know how to take the derivative of a square root function. F prime is 1/2 x to the negative 1/2 power. This is just a rewrite. Now I'm going to put that value of 36 in for x and do the math here. I know root 36 is 6. I know 2 times 6 is 12. I know my slope now is 1/12. Beforehand, I'm going to get the point. The point is the order pair 36, 6. The slope is 1/12. So now I use my point-slope form. Point-slope form, we've got to be have mastery here at point slope form, this is going to be y minus 6 equals the slope, 1/12, times quantity, x minus 36. There's my point slope form. Now remember, the original is asking me to approximate the square root of 37. It's only at this stage that I'm using 37 for x. So I've done a whole lot of work here without ever touching the number 37. And you should know that. You're going to do a whole lot of work before you're even touching the value that you need to approximate. But at this stage, pretty simple. All I need to do is put in 37 for x and do the math. Well, 37 minus 36 is 1 in most countries, times 1/12 is 1/12, plus 6 more gives me 6 and 1/12 for an answer. Every correct answer should be 6 and 1/12. Let's do problem number 2. Oh, by the way, here's my calculation. Check it out. Just so you can see how impressive you are without a calculator, if I go root 37 on my calculator, I get 6.0827, blah, blah, blah. Look at what 6 plus 1/12 is. 6.083, just a sliver above what is actual, which is important here. 6 and 1/12. It's pretty impressive. That's a pretty impressive approximation without even using a calculator. But what I want to emphasize further is notice that it's slightly above the truth. And this is an important note. Our approximation is an overestimate. This is dictated by the fact that root x is concave down. Yeah, what can the fact that it's concave down have anything to do with it? I figured it was an overestimate because 37 is over 36. That doesn't have anything to do with it. Stay tuned. So let's look at what we've done here. We've got the square root of 36, and we know that is 6. And we know the graph of root x looks like this. It passes through the order pair 36, 6. And we are using the tangent line at 36. We figured out the equation of that tangent line, and we figured out that green point, which closely resembles the actual value of root 37. Notice the green point lies above the red point. The fact that the green point lies above the red point is dictated by the fact that the red curve, root x, is concave down. The concavity of my function at the point is the dictating factor of whether I have an over or under estimate. Stay tuned. But that's what we're focusing on there. Our linear approximation is a slight overestimate since f of x is concave down. There's the estimate, there's the actual. We found that a nice approximation for root 37 is 6 and 1/12. Okay, problem number 2. Use linear approximation to estimate the cubic root of 62. So now you got to kind of be familiar, you guys, with some common square roots and cubic roots, like the cubic root of 8 is 2, and the cubic root of 27 is 3, and the fourth root of 64 is 4, etc. How about this one? What do I know? The cubic root, I got to start with an I know statement. What do you know that's in this neighborhood here that's a cubic root? I know the cubic root of 64 is 4. Yes, it's true. 4 times 4 times 4 equals 64. That's what I'm going to start with. So with that beginning, I follow the same exact steps as the last problem. I let f of x equal the cubic root of x. The cubic root of x written as an exponent. I now take its derivative, 1/3 x to the negative 2/3 power. I'm going to now plug in 64 for x. And I've rewritten the negative 2/3 power as a radical downstairs. I take the cubic root of 64, which is 4, and I square it, which is 16. and then make sure I multiply that by 3. I get 1 over 48. My slope is 1 over 48. Remember, I need two things, a point and a slope. Those two things I can create an equation of a tangent line. The point is, did you learn it from the last problem? Is going to be 64,4. 64,4 stolen right there from the original I know statement. Now it's time for point slope form. Y minus 4 equals 1 over 48 times quantity x minus 64. In lieu of that x, you're going to plug in 62 because we're trying to find an approximation for the cubic root of 62. You can do this math without a calculator. 62 minus 64 is negative 2. Negative 2 times 1/48 is negative 2 over 48. Cut them both in half, you get negative 1 over 24. Don't get crazy about yourself here and get a common denominator. This is just negative 1/24 plus 4 is just a sliver below 4. You understand? 3 and 23/24. 3 and 23/24. That's what I get as my linear approximation answer for approximating the cubic root of 62. Let's check it out, see how well we did. The cubic root of 62 is 3.957 from the calculator. We found that it to be 3 plus 23 over 24, 3.958. Look how close that is. Very, very impressive. It's impressive to me that when you do linear approximation, you're getting so impressively close to the truth. And remember the picture, the big picture here is the function cubic root of x. We know that the cubic root of 64 is 4, and we're going to use the tangent line at 64 to determine on that tangent line what the value when x equals 62 would be. Since that tangent line so closely resembles the actual blue function. The actual blue function you could just see as a sliver below what we approximated. So that's what should catch your eye. That is what a linear approximation is about when you're getting visual, like the song says, and you're picturing this in your mind's eye. Okay? Again, if a problem asks you, and they commonly do here, is your approximation an over or an underestimate? In this case, 3 and 23/24 is an overestimate. Why? Since at the location where x is 62, the function cubic root of x is concave down. It's not concave down everywhere, you guys. It is indeed concave down, as you can see here, when x equals 62. All right? There's my estimate in green. There's the actual in blue. Everybody's sitting pretty. So last problem here, and this is straight off an AP exam. Here's a hot air balloon, and it's being filled up, and I can measure the radius at a certain time. It's kind of like a sphere, can be estimated like a sphere. And you can see what's happening is as the balloon gets more and more hot air in it, its radius is increasing. So, semi-wordy here, but the volume of this hot air balloon and its radius will expand as the air inside it is heated. The radius of the balloon in feet is modeled by a differential function. We're not giving you that function. But the function is called R of t, where t is measured in minutes. Now, here's a table that has t in minutes. Maybe you've been to the balloon festival and you're watching. How long does it take to fill a balloon up with hot air? So this is probably real life data. And now you're not given radius information. Notice, row 2 is not radius information. Row 2 is the rate at which the radius is changing. I mean, picture yourself blowing up a balloon, right? That radius gets bigger. It increases quickly at the beginning of blowing up that balloon. And as the balloon gets larger and larger, the radius's rate is slowing down, okay? So these numbers should make a little sense to you. When the time is 0, at the moment I begin this process, the rate at which the radius is increasing is 5.7 feet per minute. And here's the rest of that data. Now, the question we're going to have is, we want to estimate the radius of the balloon when the time equals 5.4 using linear approximation. We're also given the fact that the radius of the balloon is 30 feet when the time equals 5. So you're looking at that, shrugging your shoulders and saying, at time 5.4, I don't know, the radius is going to be greater than 30 feet. That much I know. So I'm going to check myself on that when the dust clears. So I just have to copy and paste because I ran out of real estate here. Here is the information that you are provided, table-wise, etc., and the problem that was presented. Remember, we got to find a point and a slope. Well, the point and the slope we can steal. The point is stolen right from this yellow information, right? I get a radius of 30 feet at time 5. So the point's going to be the order pair 5, 30. The slope I can steal from the table. So a nearby point that I'm going to use linear approximation for is when the time is equal to 5. I see from the table that when the time is equal to 5, the slope is 2. When the time is equal to 5, the slope is 2. So when the time is equal to 5, the balloon is increasing, its radius is increasing at a rate of 2 feet per minute. Now I write down what I know in point slope form. The radius minus 30 equals 2 times quantity t minus 5. What am I going to put in for that t? 5.4. That's what the problem challenges me to do. I'm going to do the math here. Notice I'm going to do this by hand. These are typically a no calculator challenge on the Foster Wheeler AP exam. So 5.4 minus 5 is 0.4. I multiply 0.4 by 2 and I get 0.8 and add that to 30. ATM is an abbreviation we oftentimes use in calculus class. That stands for at the moment. At the moment. At the moment, the time is 5.4 minutes. The radius of the hot air balloon is approximately 30.8 feet. That's what we were hoping for too. Something a little greater than 30 feet. So that gives you an idea of the linear approximation challenges you have in front of you. Hope that's helpful and gives your brain a head start. This is Mr. Foster, Math Made Easy. Over and out.